Welcome back. All right, we are to the second and final part of Chapter 5, Module 5, and we are to our first specific probability distribution. It's the binomial probability distribution. You'll notice the prefix bi, meaning two. This distribution is all about there being two choices. It's either a success or a failure. For example, flipping a coin. It's either heads, a success, or a failure, tails. There's no other option when it comes to that. And so let's talk about the criteria. The experiment is performed a fixed number of times. Each repetition is called a trial, and n is the number of trials. Trials must be independent. This means that the outcome of one trial will not affect the outcome of other trials. For example, flipping a coin. When you flip a coin, the first flip has nothing to do with what's going to happen on the second flip. For each trial, there are mutually exclusive or disjoint outcomes. And as I mentioned, it's either a success or a failure. However, that's defined in any given experiment. P is the probability of a success in a single trial. Q, which is the complement 1 minus P, is the probability of failure on a single trial. The probability of a success remains the same for each trial. And I'm going to introduce this, but we're mostly, and by the way, you will definitely need your calculator for this lesson today. Doing it the old way just takes way too long. And I'm not even going to go through how to use this formula here. And so the probability of obtaining exactly X successes in N independent trials of a binomial experiment given by, and we have P of X, and you can see the combination again, where P is the probability of a success on a single trial, and X goes from 0 to N. And so for this example 7 is all about how to use your technology, your calculator. So have that ready, please. If you need to pause the video, that's fine. So we're going to be doing a binomial distribution. Now, for this first one, and I'm not going to write out every single one like this, N is 8. That means we have a possibility that, we're going to end up at 0 successes, 1 success, 2 success, 3, 4, 5, 6, 7, or possibly 8 successes in a single trial. In 8 trials, pardon me. So here's what we're saying. What is the probability? And the probability of a success is 30% or 0.3 of 5 or less. Here's what that looks like. 5 or less. Now, your calculator only knows less than. We'll deal with greater than in a minute, but it only knows less than. And we are including 5 in this case. So let me show you what we're looking up here. We're going to go to our distribution. It's right above my bars button. Your calculator may be somewhere else. Second distribution. And we're going to go down and we're going to do all these distributions this semester, but not today. We're looking for a binomial. There it is. There's 2 of them. Binomial PDF. We'll get to what that means, but we want binom CDF. The C stands for cumulative. That means we want the probability of this plus probability of 1 time plus probability of 2 successes plus probability of 3 successes all the way up to 5. And here's how we do this. Now your interface may be a little different than mine. And we'll talk about what that means here. Number of trials, that's N, 8. Probability of success is 0.3. And this is going to be 5. Now, if you don't have this interface, if you have an older version of this calculator, then it's going to be like this. It'll say binom CDF, and then you'll have 8. Let me write it down. CDF, and it'll be 8, comma, and let me show you where the comma is on this calculator. The comma is right here above the 7, comma, 0.3, comma 5. It'll look just like this. Or you have the interface that I have. Hit enter, and there's the probability of 5 successes or less. There it is. So we're going to practice a bunch of these just to get the practice. Now for this next one, They want to know there's 7 trials. 1, 2, 3, 4, 5, 6, 7. And in this case, notice in this one, we included the 5. This one, they're saying they only want less than 4. So that means we're going to go 3 and down. CDF. Cumulative density function is what that stands for, if you're curious. 7, 60% chance of success, and we want 3 and down. Notice we included the 5 on this one because it was included here with equals. But here, we're not including the 4, which means 3 and down. So the 3 is going to go there. Let's see what that looks like. CDF, again, we'll talk about PDF here in a moment. In this case, the number of trials are 7. Probability of success, 0.6. And now we want 3 and down. Those of you with the other interface will look like that. So we're getting out 2, 8, 9, 7, 9, 2. And everyone who's watching this video, you should be pausing it if you need to and actually putting this in your calculator to get the practice. All right, here we have another less than or equal to. So this is going to be binom CDF. Only 6 trials, 0.2 chance of success. And this one, we're going to include the 3. Binom CDF. Trials in this case are 6. Probability of success is 20%, 0.2. And 3 happens to be the same. All right. And if you're getting different numbers than me, try it again. In fact, I'm double checking my numbers as well. Yeah. All right. So these have all been less than, which your calculator knows how to do only. Now the equals, exactly equals, that's when we use the binom PDF, when we have equals. And that's going to be same order, 8, 0.5, 4. PDF, not the CDF this time. Meaning we're not adding up all the previous ones after before the 4. We only want what's the probability of there exactly being 4 successes. Number of trials is 8. Probability of success 50%. Exactly 4. Two, 7, 3, 4. All right. Next up, we now have greater than. That's a little bit of a game changer because most calculus, some of the newer ones, you can have it do greater than and stuff like that, but ours is only going to be less than. So here's what we're going to do with this. Let me write out all the possibilities. 0 successes, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Meaning there could be no successes, there could be exactly 1 success, 2 successes, 3 successes, 4 successes, and so on. Now here's what they want to know. They want to know strictly bigger than 7. That's 8 and up. However, your calculator doesn't know 8 and up. Your calculator knows 7 and down. And so what we're going to do is we're going to have to do 1 minus binom CDF now. And that's going to be 10, 0.4, and now we're going to do 7 and down. Here's what that's going to look like. 1 minus. We're back to CDF because we want all of them below as well. Number of trials is 10. Probability of success, 0.4. And now we want 7 and down. And please note, this is 1 minus. See, 1 minus. That gives us that. Yeah. Double check my numbers. 0.1, 0, 1, 2, 2. So we have to do the complement. So we'll have to do the complements for these as well. For this next one, again, what they want now is they want 5 and bigger. So what's the opposite of 5 and bigger? That's 4 and down. So we're going to do 1 minus the binom CDF 8, 0.9, 4. So we're going to have to do the 1 minus 8, 4. And for our last one, so 0, 1, 2, 3, 4, 5, 6. They want, oh, this is less than. So this one's no problem. So now we're back to just regular binom CDF. This will be of 6 trials, 20% chance of success. And we're including 3 in this case, right? 3 and down. Six, 2, and 3. Nine, 8, 3, 0, 4. All right. May need to practice that page a couple of times. Example 8, Larry has a batting average of 0.2. Of course, in real baseball, we would say he has a 200 batting average, meaning 20% of the time he gets a hit. X is going to be the number of hits in 5 times at bat. So there's my N. N is 5. And yeah, here's P, probability of success. How likely is it that he'll get at most 3 hits? At most 3 hits. Let's break that down. So 0, 1, 2, 3, 4, 5. At most 3 hits is going to be there. This means X is less than or equal to 3. So this is just regular binomial CDF of 5, 0.2, and then 3. Let's see what we get here. All right, so we have 5 at bats, 0.2 and 3. How likely is it that he'll get at least 2 hits? This means X is bigger than or equal to 2. So we're going to have that kind of backwards scenario here because it's greater than now. So let's write this out again. 0, 1, 2, 3, 4, 5. At least 2 hits. That means we're looking here, which means we're going to have to go the 1 minus binom CDF and 1 because it's greater than. So let's see what we get. 1 minus there we are, 5 at bats, 0.2. So I guess I just need to change this 1. All right. So basically what we're saying is if Larry goes up 5 times at bat, what's the probability that he's going to get 2 hits or more? But a 26% chance of that happening. That's because his batting average isn't all that great. How likely is it that he'll get fewer than 2 hits? So do you see it's the complement of this? Fewer than 2 is literally the 1 and down. This is X is strictly less than 2. So that's this one here. So I'm actually going to do the complement of the previous answer. So 1 minus, and remember that previous answer trick I'm going to do? That's the blue here. Second answer. That means 1 minus the previous answer. There we go. So this becomes 0.73728. That's actually exactly that. So much better chance that he's going to get less than 2 hits. How likely is it that he'll get 3 hits? This means X equals 3. So there's no less than. So this is the PDF again. PDF 5.2 and 3. Binom PDF. PDF. 0.2, 3. Not a very good chance of him getting 3 hits. Not with a 20% batting average. All right, good old Larry. All right, checking for unusual results in a binomial experiment. It's going to be the same that we had before, where we're going up and down 2 standard deviations. So as long as we're within 2 standard deviations, it's considered a usual result. We need to show that NPQ is bigger than or equal to 10. And that'll allow us to do this, assuming that it's a normal distribution. And we'll come back to that. I did want to show you these graphs here. As n gets larger, you can see it becomes more and more like a normal distribution. You can see it's skewed right here. Remember, skewed means longer tail. So skewed right, still a little skewed right, and here it's much more normal, and you can see n is increasing as we're doing that. All right. Last page for today. All right, so we have mean or expected value. Here's the formula for that. N times P. And to get the standard deviation, it's 10 times P times Q. Remember, Q is 1 minus P. So some textbooks, they don't use Q, they just put the 1 minus P in parentheses there. Okay, here we go. According to an almanac, 70% of adult smokers, that's going to be my P, which means Q is 30%, or 0.3. Started smoking before turning 18 years old. There are 300 trials of the experiment, round to the nearest tenth as needed. Find the mean. Well, the mean is N times P. I think it's 210, but we'll see. 300 times 0.7. Find the standard deviation. And I'm going to use my memories on my calculator here in a second. So I'm going to do square root 300 times 0.7 times 0.3. And what I'm going to do is I'm going to store this off into a memory. Let me show you how to do that. Can you see the little green letters above? I have an A, a B, a C, D, E, F, and so on. Those are all memories. And the way I store this number is I go to store, S-T-O, and then I select. I'm going to select A. You can select whatever, S for standard deviation if you want, it doesn't matter. And then I hit enter. And now the letter A is my standard deviation. Now, what I'm going to do in the notes here is write this as 7.937. And I'm going to remind myself I stored that into memory A. That's a nice trick, especially when we have to start storing lots of memories and we have A, B, C, D, and I'm trying to remember which one's what. So I just label it. That's what I'm putting. And so let's interpret the mean. It is expected that in a random sample of 300 adult smokers that 210 would have started smoking before turning 18. That's how we interpret that. Next part, perform the check on this on the condition that allows us to conclude the binomial distribution in this case is approximately bell-shaped. Now, that is this condition here. That's the NPQ is bigger than or equal to 10. That's what they're asking for on that one. So NPQ is 300 times 0.7 times 0.3. As long as that's bigger than or equal to 10, we can assume it's big enough to go for it. So 300 times 0.7 times 0.3. 63. 63. And once again, it just has to be bigger than or equal to 10, which it clearly is in this case. So, oh, bell-shaped. So would it be unusual to observe 255 adult smokers who started smoking before 18 in a random sample of 300 adult smokers, and why? Well, that's going to come back to these. So we're going to have to come up with our lower boundary and our upper boundary. So the lower is the mean, which is 210, minus 2 times the standard deviation. Now, of course, I'm not going to use 7.937. I'm going to use my memory allotment A for that. So 210 minus 2A, because I stored A is that number. And we're going to round this off to the nearest person. 194 smokers. Our upper is going to be the 210 plus 2 times 7.937. So 210 plus 2A. So we'll say 256. 226, pardon me. Ooh. So meaning if we had a group of 300 smokers and want to know how many of them smoked before the age of 18, then a usual amount out of those 300 would be between 194 smokers and 226 smokers. Anything less than 194 is unusually small amount, and anything more than 226 would be unusually large. So they want to know, is 255 unusual? 255 is definitely outside this range here. 255 is definitely bigger than 226. So 255 smokers would be unusual. Not too bad. Some of you may be shying away from using the memories in your calculator. You're like, why do I need to do that? After a while, it really does become a huge asset to be able to know how to do that. And it's not that hard. Last example for today. Example 10. According to a report, 66.2% of murders are committed with a firearm. There are 400 trials of the experiment. So here's my P, which means Q is going to be 1 minus that. We'll get that in a second. Here's my N. And I'll use a different color, make it a little bit more distinct. In fact, let's figure out Q right now. Q is going to be 1 minus 0.662. So Q, 338. Find the mean. Mean, if you remember, is N times P, which is going to be 400 times 0.662. This is 264.8. Standard deviation, again, is the square root of NPQ. We get square root of 400 times 0.662 times 0.338. And I will also be storing that off into a memory. Square root of 400 times 0.662 times 0.338. Store that as A again. 1.46. So it is expected in a random sample of 400 murders, we'll say 265, I'm rounding off the mean there to interpret the mean, would have been committed with a firearm. Perform the check on the condition that we can say it's approximately bell-shaped. That's the N times P times Q. You see that's exactly what's under the radical there? So I could actually just square this. But let's double check. 400 times 0.662 times 0.338. It's the same. So we're getting about 90, which is definitely bigger than or equal to 10. So definitely bell-shaped. Last part, would it be unusual to observe 294 murders by firearm in a random sample of 400 murders, and why? So now we need to do the plus or minus 2 standard deviations. So the lower for usual is going to be the mean, which is 400. minus 2 times the standard deviation, which I'm going to use the letter A in my calculator because that's where I stored it. Did I actually store it? Yes, I did. 9.46. Let's see what we get. 400 minus 2A. 81. The upper 400 plus 2 times 9.46. I'm using the wrong numbers. Let's do it again. I was using n instead of the mean, so I should be using that number. So there we go. Lower should be the 264.8 minus 2 standard deviations, which is 9.46. So yeah, 264.8 minus 2A. That's looking better. So 246, we'll say murders. In the upper 264.8 plus 2 standard deviations. $264.8 plus 2 standard deviations. 283. 284. We'll round that off. Murders. So let's go back to our actual question. Would it be unusual to observe 294? Wow, that's definitely above our upper range here. So 294 would be unusually high. That is a binomial distribution.